which is we focus on the patients who actually have cancers, and it is the proportion of that the model predicted it's because the patient is actually have cancer, so it is the proportion of the model predicted correctly within all those actually have cancer patients number. And this specificity is is called the true negative rate. It's focusing on this row is the model correctly ruled out those patients who is healthy within all those healthy patients. And also the precision is focused on columns. It's the model predicted within all those predicted as cancers patients, how many of them are actually have cancer. And the last one is called the negative prediction value. This column is when the patient is actually healthy and within all those patients are healthy. So it's really confusing. Confusion rates. So this is the basic for us to understand this AUC ROC, which is a very popular or is the main evaluation matrix for if you have a model, machine learning model, you want to know if the model is the model performance is good or not. Usually people will have this AUC ROC. So let's quickly run through how it works. So basically it computes two values. One of them is this true positive rate, which is the sensitivity, and the other one is the false positive rate, is this 1 minus specificity. So true positive rate is the model detected all those cancer patients within actual cancer patients, and the false positive is the model predicted the patients is healthy within all actual healthy patients. So it calculates not only those two numbers at once, it calculates in different decision threshold, which is called tau. So this tau is a range from 0 to 1, and within for each of these decision threshold, it computes the two numbers, and it has this plot as the false positive rate as the x-axis and the true positive rate as the y-axis. And then it will have this curve. It's called the receiver operating characteristics curve. And then the AUC value is the total area under this curve. So it means that it averages the performance at every threshold. But it causes two problems. So the first problem is not all those tau is meaningful, especially when those extreme taus, for example, is extreme large tau, it's very close to 1. It means that it just set every patient as cancer patients. And also the extreme small decision threshold means that it just treat everything as healthy. So it's actually not very meaningful in practice, especially when you try to use it in the clinical use. And the other question is what the clinicians mostly care about is actually not the average performance of this model. It's actually the model, how many mistakes the model make. For example, how many patients are missed the diagnosis of cancer, or how many healthy patients are misdiagnosed as cancer. So, for example, if AUC equals 0.9, it's actually is an excellent model performance, but it can also include maybe 20% of the false negative rate, false negative cases, which means 20% of the patients are missed the diagnosis of cancer, and also 25% of the healthy patients are diagnosed as cancer. So it's in practice, it's not that good. Excellent. Yeah, I think we can go to the next slide. Yeah. Right.
So based on the definition of the ROC AUC. In general, we have a definition for the high ROC AUC. So by default, we say the root square of pi is a standard high ROC AUC, which means it's equal to 0.785. And in this case, we have a curved blue curved line here, define all the points can be connected to achieve this ROC AUC. And all the points here have either at least the true positive rate equal or larger than 0.71 or true negative rate equal or larger to 0.71. So all the points connected above this blue line can have a great ROC AUC score, but this doesn't mean any great performance based on our previous discussion. So what the high ROC AUC does not say. So from this figure, we can say a high ROC AUC like 0.8, about 0.8, and not only include all the good result, but also it includes some bad areas plotted in red. So in this area, all the prediction performance should be very bad, but it already included in the total score for the ROC AUC. So the classification result could be very poor, also included in the score. And the other hand, the ROC curve and its AUC provide no information about the precision and the negative predict value. So we can trick the model in two different way. We as the previous slide, we have at least one score above 0.71, so we can predict everything to positive to have a very good true positive rate. But in this case, we lost the evaluation for the false positive one. And the other way to trick the model is to predict everything negative. In this case, we can also have a great value for the true negative rate, but we may miss the false negative cases here. So there are two extremely cases for the high ROC AUC score, but the model is not predict the results very, very precisely. So in this paper, the author proposed to use the massive correlation coefficient to replace the standard evaluation way with the AUC ROC. So how can we calculate the MCC score? So it's calculated by the geometric mean of the correct rate minus the error rates. So the formula here is the first part is the root square of all the correct rates product minus the root square of the error rates product, square root of the error rate. So the first part evaluates all the great values, the positive, true rates, and the second part here are all the false and the wrong values. So we can derive the lower, the standard representation of the MCC formula from the upper part. So how can we calculate this rates? In the paper, it mentioned a 2x2 contingency table. So here I highlight each pair of this positive predict value paired with this false discovery rate. So we can simply use the true positive rate, 1 minus the true positive rate is the false negative rate. So the circle in the solid circle and dashed line circle, they are paired with each other and they can add it to 1. So that's why this the MCC score can have a worst minimum value from -1 to the best maximum value of 1. So here is how it can be calculated. Okay. Maybe next one. Cool.
I have a question.
Yeah.
So my question is, do you do any pre-processing? Because usually you can divide your data set into different quartiles.
Yeah.
And say, let's say, if I remove this 10%, my ROC will equal to 0.9. So because I would suggest you to do some RMSE, some mathematical calculations to understand which points have big diversity with the average ones. And then if you remove these points, for instance, it's also quite good. You can say that my AUROC will be equal to 0.9, for instance. To find out this lag point, then you have some problems. And then you can consider these points further on, what to do. Because usually you need to separate your data sets into different quartiles.
So to calculate the AUC or any kind of matrix.
Let's say your AUROC is equal to 0.7.
Yeah.
How many points you have that is the difference with your average, for instance, is 0.4. You don't have this information because you just have one average value.
So you first group
You don't know the behavior of your points.
The data.
You just have one number, but how these points are grouped with your average, you don't have any idea. So in order to have this idea, I suggest you to do some pre-processing, calculate RMSE, MSE, etc., in order to understand how the points are distributed compared to your average.
Great point to have another calculation with the data set.
It's just calculation. It's very simple. But mathematically, you can present the behavior of your points.
So you could like project them onto the AUC curves or something.
So let's say you have 0.7,
Yeah.
maybe you have, let's say, 2% of points very far from your average. Or maybe all of them are very close.
Yes.
You don't have this information.
In the AUC picture.
Yes.
Yeah.
In RSC picture. So that's why if you can do such RMSE, MSE calculations, then you will get also this information.
Got it. Yeah.
Do you understand what I mean?
Yeah. That's right. To do it.
Because now you don't have any idea about
Right.
the distribution of your data point.
Right. And how much the easy ones versus the hard ones.
Yes.
Yeah. Okay. Yeah. No, that's a good point. I think we're going to find lots of issues with the AUC, I'm sure, as we go through this. So that's a good place to start. Is someone on Zoom?
Yeah.
Oh, you're very loud. Okay, cool.
Sorry.
Good. Go ahead.
Okay. So this next segment of the paper kind of just tries to communicate and explore the relationship between the MCC and AUROC. So the first point they wanted to make was that the MCC is affected by class balance. So along the x-axis here is prevalence, which is just the fraction of the data set that belongs to the positive class. So 0.5 is 50% of the samples belong to the positive class in this case. And they just pick 3 different pairs of true positive rate and true negative rate values, because those are not affected by the prevalence. And then they plot the curves of the MCC values. So as you can see, when the classes are heavily imbalanced, the MCC drops a lot. And when you have different values of the true positive rate and true negative rate, it can skew this curve a little bit. So just trying to give you a little information about that relationship before we go and talk more about ROC. Next slide. Thanks. So this plot is showing, it's an ROC curve, or the same plot that an ROC curve is plotted on, the FPR and TPR. And then it's colored, they just color the top left side. It's colored based on the best case scenario MCC value for those coordinates. So for every coordinate on this plot, there's there's multiple values of MCC that could be like related to that position, or there's like a AUROC value that is associated, that could be equivalent or could be present with multiple MCC values. And the color in here shows the best case scenario. So the highest possible MCC value for that point. And it just gives you an idea of if you were looking at an AUROC curve, what would be the best case scenario for an MCC value given that curve, so it's a lot more, I think, stringent than we would assume just looking at a normal AUROC curve. Next slide. So they also then picked 3 different points on that previous plot and that are in different areas of plot. So if you can see at the bottom, there's a point in the top left corner, one kind of the center, and one kind of in between those two. And these subplots A and B, C and D, E and F, those pairs on the rows are showing the same data, which are just in a histogram versus box plot. And these are all the MCC values that can exist given that false positive and true positive rates that were in the previous plot. So they kind of are exploring a little bit of the distribution of values for MCC that you could get for any given kind of AUC value. Next figure. And they're highlighting like that non-linear relationship that exists here. It's not a clear relationship, very easy to define one. Yeah, so this figure is showing very similar information where we have MCC values on the x-axis and AUC values on the y-axis. And they did 70,000 simulations of different possible like binary classification tasks. And the thing that's main takeaway here is the AUC goes above 0.5, so you're doing better than random guessing. Any given AUC value, so maybe pick 0.75. If you look at the data points that are at the level of an AUC of 0.75, their MCC value can be as small as 0 or as high as maybe 0.6. So there's a really wide range of MCC values here. And a point they really want to emphasize is that even if your AUC is good, your MCC value can actually be, your MCC score can be really poor, near 0. When I think a lot of people would say an AUC of 0.75 that's decent. But if you look at an MCC value, so if you calculate, the MCC value of 0.5, that will guarantee you have at least a decent AUC score of 0.75 up to 1. So one of the main takeaways from this is how what kind of assumptions you can have about the quality of the classifier by looking at these 2 metrics. So if you look at MCC and you look at a score, you can know that the AUC is going to be, you can have a better idea of what the AUC would look like given an MCC score. So if the MCC is 0.5, you can say, okay, well, I know that's a decent classifier at least, because the worst the AUC could be is around 0.75. But if you have an AUC of 0.75, you have really no idea how good of a classifier it is because the MCC could be so low, and that MCC incorporates more information. So I think the takeaway from this plot is just the MCC tells you more information than the AUC does. Okay, next slide. And this is kind of all these figures are kind of reemphasizing that point. For each plot, the AUC is on the y-axis, and on the x-axis are these different values. These first 3 on the top left are the normalized MCC, which is just, instead of being the score from -1 to +1, it's just from 0 to 1. And the other subplots are true positive rate, true negative rate, and other scores. And in each column, going from left to right, is when the data set's really negatively imbalanced, balanced in the middle, or really positively imbalanced. And so really one of the main takeaways here is that if you look at, for example, you have a balanced data set, and so let's look at subfigure D. You have a balanced data set, and you're looking at a true relationship between the true positive rate and AUC. Given in any AUC, like, I know it's really small, but like 0.75, the true positive rate can range a lot. It can be as low as maybe 0.2 or as high as 1. That's a huge range. So this is kind of re-emphasizing and retelling the story, like there is a lot of information you don't know by looking at AUC. And so, judging, it's kind of, you can't like judge a book by its cover. You can't judge a classifier by AUC. And then another interesting point they point out about the positive predictive value and negative predictive value on the right 6 subplots is they kind of have those weird like peaks, or like, I guess you call them peaks at 0 and 1. And just how, if you're looking at the AUC of the positive predictive value can be a wide range, and it can jump like, up to like having a positive predictive value of 0 or 1. So just kind of some weird relationships going on they want to highlight, and to really emphasize, like, you cannot put that much weight into AUC. I think that's all my slides. Yeah.
Thanks, Matt.
Yeah, great. So basically my slide tries to summarize and wrap up Matt's points using some practical examples. There were 3 use cases described briefly in the bottom right, where electronic health records were used to try and predict whether patients survived or not using binary classification. Random forest models were trained 100 times, and the average results are presented here for each use case example. And given the definition, ROC, AUC used all of the tau thresholds, whereas MCC used the heuristic traditional 0.5. Similarly, for the 4 basic rates, or otherwise the TPR, TNR, PPV, and NPV. And again, basically to just echo what Matt was saying with all of his slides, MCC did a better job representing the existence of a poor rate metric, whereas ROC AUC didn't do such a good job representing that. Whereas, especially for the first and second use case examples, the ROC AUC, if you look at them in a silo, like on their own as one metric, you might be a bit deceived thinking like, oh, this model did fairly well. Whereas if you go to look at the 4 basic rates, you'll see at least one of them is pretty low, like astonishing low. So this slide, again, just shows that MCC does a better job highlighting if one of the basic rates is low. But importantly, it's good to note that just because it highlights that one of them is low, it still doesn't tell you which one is low. So it's still good to look at these 4 other metrics. It's just if you're going to use one summarizing metric, MCC seems to be better when compared to ROC AUC.
Great, thanks, Alan.
Yep, so I'm just gonna basically summarize kind of what everyone else was saying. So the main strength of this Matthews correlation coefficient is that it encompasses all of the 4 basic rates of the confusion matrix, instead of just like kind of disregarding the positive and negative predictive values like AUROC does. And it like a high Matthews correlation coefficient necessarily means that they're all good. So it's defined using the same inputs as the ROC curve, which is great. It's just like standard machine learning confusion matrix things. And the Matthews correlation coefficient is relatively robust to class imbalance. And then next slide. And then the limitations are kind of like nitpicky, I guess, because Matthews correlation coefficient is just pretty clearly better than AUROC. So it doesn't indicate why the model performs poorly, which neither does any other like catch-all metric. It just indicates one of those 4 basic rates is probably not great, or at least one. So it's better to figure out what is actually wrong with the predictor. You need to look at those. And it's based on like a given cutoff value, whereas ROC considers all different thresholds that you could have. And it can also be undefined in certain cases, but that doesn't really matter as much because you can just like, in those certain instances, you can like define that to map to a certain Matthews correlation coefficient.
Awesome. Thank you all for summarizing. That was a really good summary of the paper. So I guess I want to start us off with maybe some initial reactions. I'm gonna stop sharing so it's easier to see everyone on Zoom here who's talking. But I kind of want to get an idea. This is probably new for most of us in the room, and I've never heard of MCC before, even though they claimed that there was lots of papers out there that were citing it. But and obviously all of us have used AUC in our work, knowing that there are some limitations. Kayvon was in my office for like an hour yesterday, rattling off. I asked him what he thought of the paper, and he just rattled off like all his hatred of AUC. That's not what I asked, but that's okay. Anyway, so let's see initial reactions. What do we think of this MCC? Do we think they're just like making stuff up? Do we think it's going to be useful? Would you use it in your work? Let's go there. You all run models, so what do you guys think?
As I said on Slack, I'm not a fan of MCC or other metrics. I only use one cutoff value. Because to me, including this manuscript, if you're comparing a MCC versus AUROC or AUPRC, I think you're comparing apples versus oranges. Because I believe in the very beginning of biomarker or model development, we are not sure which is the best cutoff. Although I know that computer science people sometimes they only rely on 0.5 tau value, the cutoff value, which is sometimes underuse the other cutoff because clinically, say you have a biomarker to tell if you have myocardial infarction or not. We are not, as a clinician, we are not fixed with only one threshold. We are going to try to use all of the possible threshold. If you have a lower threshold, we can use that to exclude patient. We can send patient home instead of just stick with one cutoff value. So I would say this is the first thing that if you're only comparing one matrix, you're going to miss the forest. You only focus on the tree. So I will argue that early on in the development, you don't know what's the best cutoff, and sometimes you have imbalanced data, right? Like I know in the discussion you mentioned that imbalanced data set. So that's when I would argue that the MCC or AUPRC, even the AUPRC has this prevalence issue. So again, clinically, if you presenting a 0.5 AUPRC, I'm going to ask you what's the class ratio, what's the positive rate, what's the prevalence. And then if you present in the AUPRC, I'm pretty confident and I know what to do with a matrix or model with a 0.7 AURC. That will be easier for me to understand. So I would say early on when you're comparing the model, if you just use, MCC, that I think that will be very problematic. Having said that, I also paste something in the chat saying there's only alternative way to use AUPRC. You can use partial AUC. The partial AUPRC means you just use a certain area because sometimes say in the frontline healthcare settings such as ER or outpatient clinic, we want to use a tool with acceptable sensitivity, and then with that we can just evaluate the average specificity. How can we use this acceptable tool with acceptable sensitivity, and we can use the tool with better specificity to rule in our patient, say for further expensive or more invasive procedure for our patient to make final diagnosis. So if we have a perfect diagnostic tool, that will be easier. But daily practice, we don't have perfect tools. So I would say we have to use what we have. That's the past. So that's the first thing that come to my mind. The second is the some of you mentioned that AUROC disregard false negative or false positive. I don't know which one we want to say that, but again, sensitivity and specificity also include that part. So I would say that's also something AUPRC or AURC could be useful. In addition, during the past, I have many experience have the crossover AUPRC or AURC. So if you imagine you have a crossover curves, but at some point you have the same MCC, I think also in the paper they also have this example. So what would you tell? You have the same MCC, so if you just use MCC to pick the model, you're gonna miss them. So this crossover thing is also relatively common. I wouldn't say it's really common, but I think at least our team has several experience in the past. So having said that, I think after all, I don't think we can rely on one matrix, but to be honest, MCC is there for a while, and people treat that as a categorical correlation coefficient. If you know, correlation coefficient is some kind of very vague evaluation, like how correlate with between one and two the other variables. So some people use that as the beginning as well. So I would say I also try to find if there's any people try to use the area under MCC. Say you have different cutoff value. Can you use the area under MCC? But since it's not integrable, and since the mathematical property of this kind of different, MCC with different cutoff is not very good. But I would say I still find some people using like the maximum value of MCC to pick out the best threshold. I would say this is a better way, because in the past, some people use Uden index and they treat sensitivity and specificity the same weights. I wouldn't say it's the best way to do that, but I would say maybe MCC could be used later. After you figure out what model to be used, you can use MCC to find the maximum MCC and then to find the best threshold for that model. And that's what I think. I'm not a fan of MCC. I'm not a fan of AUROC either. I just think we just don't rely on one or two matrix to decide which model to go after. That's my opinion.
Yeah, those are some really good points. I agree. We definitely need more than one model, right? I do want to frame based on kind of your first point and the last thing you were talking about there. Let me frame maybe our discussion, because there's a lot of points where you could use these metrics, right? And maybe let's focus on the very end. So let's say you have a model, it's binary classifier, it's going to predict probabilities between 0 and 1. Ideally, you have a validation set, and if you wanted, ideally, your model is just learning to map things that are 1 closer to 1 and things that are 0 closer to 0, which is why we traditionally use the 0.5 threshold. There's no magic in the 0.5 threshold. If you wanted to set a different one, to KFC's point, you could use a validation set, and then you could use whatever score, AUC, a combination of these metrics, MCC, whatever, to pick your best threshold. So let's say all of that's been done, and we're now evaluating a model where we have one threshold, and it is binary classifier. So it is saying everything is 1 or 0 that we're getting out of it. So there's one confusion matrix that we're dealing with, there'd be one AUC value, and then therefore one MCC value as well. So let's maybe frame our usage after that point, so that, there's a lot of things that we could talk about there, but let's assume that we've set a threshold, whatever that threshold is, and then go from there. Other thoughts, reactions? Room or on Zoom?
I did have one. When I was working on that drug combo project, I had relatively few negative cases. So it seems like from the MCC algorithm that you had on there, it was going to actually pretty harshly penalize anytime that I don't have a pretty high true negative rate. So in that case, is it still appropriate to use the MCC, or should I stick with an F1 score?
That's a great question.
I don't know.
Yeah, what do we think? We have super imbalanced class data.
Did they hear me?
Yeah,
so are you comparing the models? Are you trying to use MCC to pick the best model? Is that what you're saying?
I was trying to evaluate a binary classifier that I had in the pipeline, and I had used F1 score because the ROC AUC just wasn't telling me enough. So I'm wondering if I had used MCC in place of F1 score, would that have been appropriate, or would it have been too harsh considering I didn't have a lot of true negatives to add into that equation? Or negatives at all, yeah.
I'm just wondering because again, part of the MCC include the positive and negative predictive value, which are also highly influenced by the prevalence or the case ratio. So in your case, if you have lots of negative cases so the negative predictive value will be high by definition. It's math. It's not
The
depend.
opposite. I didn't have a lot of negatives.
Oh, really? So that's because the model is not good enough either. So that could be, but I don't have a good answer. But again, if you have an imbalanced data, maybe we should just treat the imbalanced data first, and try to find the best way to train a model first. Now you could just oversample or do some, use some loss function to deal with that. So after that, you could just evaluate on the validation data set.
That would be your recommendation as well. Fix the imbalance and then.
This is where it goes.
About Matt or Alan, any thoughts from you guys just on MCC, either to Morgan's question or just MCC in general?
Yeah, sure. I mean, I was going to mention pretty similarly to what KFC had talked about that when we were looking at MCC versus ROC AUC, the basic rates all had that heuristic of 0.5, whereas ROC AUC considered all possible thresholds. But I liked that KFC, you mentioned that there's different ways to incorporate AU ROC, whereas you could weight specific regions or do partial or whatever you wish to do there to maybe try and address not calculating these extremes if that's if you're not expecting to use that in the final model or some sort of threshold that seems unreasonable, you could just exclude it. So yeah, I thought it was weird. I think saying that you're comparing apples to oranges was appropriate. So that was the only thing that really stuck out to me. It didn't seem like a reasonable comparison, although this is the first time I've heard of MCC or seen it used in practice too. So it seems interesting, but it's also trying to say which single metric does the best job when you have to use 4 basic metric rates already anyways. It's kind of what's really the benefit of just choosing the best of something that's not already sufficient on its own. It seemed a little silly.
Yeah, my thought is depends on what I'm trying to accomplish with the metric. So if I'm really trying to understand my own classifier, and then I really like just looking at a true positive rate, false positive rate, positive predictive value, and negative predictive value, and to understand things. And it's a lot easier for me to interpret what that means for the clinical context. So a positive predictive value in this case means this, or But if I'm trying to compare, multiple classifiers or some other sort of comparison, then it's really nice to have a single number to compare, versus looking at 4 different tables and, that gets out of hand. So sounds like, MCC is something that I would definitely use in the future to compare multiple things with a single number. I think it sounds like could be a better way to do that.
Yeah, that's a really good point. We do that a lot with AUC traditionally, but this might be more comprehensive to some of the points in the paper, especially when we have class imbalance. Ling-Ray, Wenting, how about you guys? What do you think?
I think most of the points have been covered in the discussion, yeah.
No other?
Yeah, I feel like the distance thresholds seems a more area to explore or be more meaningful because first off, I think this decision threshold is some relationship between the imbalanced data because that's most of us are dealing with. So I was inspired by Dr. Chen about the using the different MCC scores to decide the best a different MCC score within different decision threshold to decide this threshold. I guess maybe this is more meaningful to discuss. Then, because for all those things you can just report them. It's just the one column in your table. So yeah, that's my thought.
So it'd be more useful in picking the threshold if it were to deviate from 0.5 than it would be otherwise. than AUC, because AUC is obviously threshold agnostic.
Because AUC just mix everything together.
Yeah.
So in this paper they mentioned that they only use the threshold of 0.5 as the MCC. So maybe we could like try different decision threshold for this MCC and to see what else information can get.
If you have a validation set.
Yeah.
Jet, how about you? Jordan, any thoughts?
Yeah, I think it's mostly been touched upon about like using it for validation, like when you need one metric or like early stopping and things like that.
Okay, let me pose a different question. So here we have MCC. We're saying like, okay, maybe it would be useful for some things. Maybe it's better at AUC at some things, but also AUC takes into account this this threshold-based approach, right? So given that we're kind of rethinking AUC and its use cases and limitations, what is AUC really telling us, and what would be like the right use cases for that going forward, where that would be the better metric over any of these others? Is there any instance where we would care about AUC alone, given that we just talked about how you need to use all of them in combination?
I think if you only have like one value, then AUC is better for maybe like figuring out thresholds, or like if you have a classifier and it's not performing well but it has a high AUC, maybe you can just change the threshold to make it perform well, whereas like one MCC value won't tell you that.
True, you'd have to, with a validation set, like, and whatever, but yeah, you'd be able to tell. I guess I always explain AUC as a level of confidence. I don't know what you guys think of this, but if your model is, let's say we use threshold of 0.5, it doesn't matter what your threshold is, but your model could be predicting everything at 0.51 and 0.49, and like your MCC values, your true positive, true negative rate, all those are going to be exactly the same as if your model was predicting everything out of 1 and 0, right? Like those values are all based on the threshold. AUC is the only metric, or AUPRC, those two metrics, we're going to like tell you based on a specific threshold, like how confident is my model. And if you have a high AUC, your model's probably more confident. And if it's predicting everything at 0.51 and 0.49, it's not very confident at all. And maybe we shouldn't be, confident in it. Kind of building off of what Joe was just saying in terms of thresholds there. So what do we think about, that or anything else related to AUC?
I think that's a really good point, especially because I believe earlier it was mentioned that there was if you're looking at the charting for AUC ROC, you can maybe tell a little bit about how many hard cases versus easy cases there are. Or like you were saying, like if the threshold is 0.5 and everything's like either 0.51 or 0.49, your model might have a lot of ambiguous cases, whereas then maybe this is indicative or not of like if you were to use an external data set, it would struggle a lot more.